We have found how to find out the effective nuclear charge, and we have done what the effects of the effective nuclear charge are. And we discussed that as we move down the group, the effective nuclear charge actually decreases. That is, whenever we move down the group, then in that case the number of shells in the atoms increase, and as the number of shells in the atom increase, the effective nuclear charge decreases. Is that clear? Be very clear, the increase in atomic number is not the same as increase in shell. When we move across the period, there also atomic number increases, but that does not lead to increase in shell. The shell increases only when the atomic number increases by a certain value, a fixed value. एक atomic number increase करने से shell change नहीं होता, ठीक है? So the word is these effective nuclear charge decreases down the group because there is an increase in number of shells. Across the period, atomic number increases, but the electrons are being added in the same shell. And when the electrons are being added in the same shell, the effective nuclear charge increases across the period. But when you move down the group, the effective nuclear charge decreases because the number of shells is increasing. And that is why when we move down the group, when we move from sodium, potassium, rubidium, cesium, francium, we find the effective nuclear charge is decreasing, and the decreasing in the effective nuclear charge is decreasing the ionization energy. It is decreasing the electron affinity. It is decreasing the electronegativity, but the size is increasing. So this is what we have as a general trend in the periodic table. As we move down the group, the size increases. The ionization energy, the electron affinity, the electronegativity decreases. Now, we are going to talk about a very special case. Now, this special case happens to be that when we talk about aluminium, gallium, and indium. When we go along from aluminium to gallium, we find that there is an increase in the effective nuclear charge according to the Slater's rule by a value of 1.5. There has been an increase in the effective nuclear charge. Now, before we get along that what happens due to the increase in the effective nuclear charge, we need to know why there is an increase in the effective nuclear charge. Let's talk about the periodic table till this point. When we talk about aluminium, here we have sodium, then we have magnesium, and then we have aluminium. Sodium has an atomic number of 11, magnesium has of 12, and aluminium has of 13. When we talk about gallium, we have here potassium, we have here calcium, and the important thing is between calcium and gallium there are 10 other elements.
Yes, sir.
There are 10 D block elements between calcium and gallium. Now when we talk about these 10 elements, they have a peculiar thing. Here the configuration happens to be 4s2. This is 4s1, this is 4s2. But from here till here, the s orbital remains as it is, and the electron in n-1 d orbitals are increasing. The configuration here is 4s2, 3d1. This is 3d2, this is 3d3, this is 3d5, 4s1. This is 3d5, 4s2, this is 3d6, 3d7, 3d8, 3d10, 4s1. This is 3d10, 4s2. So here the electrons are being added in the n-1 d orbital. Clear? Electrons are being added in the n-1 d orbital. Right, put it in. Since the electrons are being added in the n-1 d orbital, we find that here the shielding effect is going to increase with 0.85 at each step, because n-1 has a shielding effect of 0.85. And the nuclear charge will increase by 1. So at each step, there will be an increase of 0.15 in the effective nuclear charge. Calcium कितना था? 2.85. Scandium 3. Titanium 3.15. Vanadium 3.0. आगे
3.45. चलिए हम 0.15 से बढ़ते हैं.
फिर यहाँ पे 0.65 ऐड हो जाता है.
Yes sir.
ठीक है?
Yes sir.
0.8 ऐड हो जाएगा. आएगा जाएगा. यहाँ पे 4.5 नहीं आएगा इसका. 0.65 ऐड होगा. यहाँ पे
65 भी ऐड होगा.
Because यहाँ पर जो इलेक्ट्रॉन गया है वो ऑटोमोस्ट शेल में गया है. यहाँ पर it is being filled in the D n-1, तो इसका स्ट्रेनिंग कांस्टेंट 0.85 का है. बट यहाँ से यहाँ it is going in the nth shell. तो यहाँ पे स्ट्रेनिंग कांस्टेंट 0.35 का है. तो यहाँ से यहाँ the difference will be 0.65. इन सब के अंदर डिफरेंस 0.15 each है. यहाँ पे डिफरेंस 0.65 का आएगा. Okay. While moving from calcium to scandium, we add an electron in the n-1d orbital. For n-1d orbital, the screening constant is 0.85. From calcium to scandium, Z here is 20, here is 21. Nuclear charge. So, nuclear charge increases by 1. Okay? Here, the electron is being added from here to here in n-1d. For n-1 shell, the screening constant is 0.85. So from moving from here to here, the screening constant increases by 0.85. Okay? So when we say sigma increases by 0.85, Z star increases by 0.15. So from calcium to scandium it increases by 0.15, 0.15, 0.15 at each step. But when we move from zinc to gallium,
0.65.
Zinc to gallium, atomic number increases from 30 to 31. When you talk about sigma, the electron has been added in the outermost orbital. Okay? Electron has been added in the outermost orbital. Now moving from potassium to calcium, the nuclear charge increases by 1 unit. An electron is added in the outermost shell and the configuration becomes 4s2 from 4s1. The shielding constant for each electron in the outermost shell is 0.35. Hence, the overall shielding constant increases by 0.35. Hence, the effective nuclear charge, which is atomic number minus the screening constant, increases by 0.65. Z increases by 1. Sigma increases by 0.35. So Z star increases by 0.65. Next step. On moving from calcium to scandium, the atomic number increases by 1 unit. The electron is added in the n-1d, that is the 3d orbit subshell. The n-1 shell has a shielding constant of 0.85. So the overall shielding constant increases by 0.85, the nuclear charge increases by 1, and so the effective nuclear charge increases by 0.15. The same trend continues till zinc. That is, at each step there is an increase of 0.15 in the effective nuclear charge over the 10 D block elements. Hence, there is an extra 1.5 unit increase in effective nuclear charge on moving from calcium to gallium as compared to
magnesium to aluminium.